By the end of this video, you're going to be simplifying radicals like they're nothing, and in about 30 seconds, here's how this video is going to get you there. We're going to be doing 5 problems in this video, and they'll be getting harder as we go. So we'll start off simplifying a few square roots, and then we're going to deal with a cube root. And after that, we'll go back to square roots, but now we're going to have a fraction inside, and then we'll combine all that gross stuff together, and we'll do a cube root with a fraction inside. So you and I are going to go through all of that, and then after that, I'm going to give you a problem to try and answer in the comments, and by that point, it should honestly be breezy. And if you're looking for the notes for this video, which, I wouldn't blame you, they're looking pretty good, those notes are linked in the description. Also in the description, I have an extra video where you and I will go through and simplify 10 more of these radicals, but I'll talk more about that at the end of the video. So we're going to start off with this first problem here, the square root of 27 times x to the 4th times y to the 5th. Now, you may know how to simplify a square root when you just have a number, but when you add in these variables, well, how does that change things? Well, what we're going to do to start off simplifying this radical is we're going to just break it up. We're going to do the square root of 27 times the square root of x to the 4th times the square root of y to the 5th. And this is something that's completely okay to do. This is still equal to this. It's just that it's much nicer to look at it like this because then you can focus on each piece separately. So let's start off by focusing on the square root of 27. What's the largest perfect square that we can take out? And well, remember our perfect squares are. That's 1, 4, 9, 16, 25, 36. It's all the numbers that we can take the square root of and get something nice. Like the square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, and so on and so forth. You get the picture. So which of these can we take out of the square root of 27? Well, we can take out a 9. So this can break up into the square root of 9 times what will give me 27? Well, 9 times 3. And the square root of 9, that's just 3. So now we have the square root of 27 already simplified. So that's nice and all, but you might be like, well, how does this all change when we start trying to simplify square roots with variables in them? And well, not much changes. We're still trying to take out the largest perfect square that we can, but you might be like, well, what's a perfect square when we're talking about variables? So let's talk about that. Perfect squares for x are x squared, x to the 4th, x to the 6th, x to the 8th, and so on and so forth. And the reason why is because we can write x squared as x to the 1st being squared. We can write x to the 4th as x squared being squared, and we can write x to the 6th as x cubed being squared. And that pattern continues for all the other x's that have a power that's a multiple of 2. From this, you can see that the square root of x squared is x to the 1st power, the square root of x to the 4th is x squared, and the square root of x to the 6th is x to the 3rd power. And to remember how to do this, really all you're doing is you're taking this power and you're dividing it by 2. So dividing it by 2, you get 3. And you can remember to divide it by 2 and not any other number because a square root technically has a 2 out in front of here. And you'll see later when we talk about cube roots, you're actually going to be dividing by this 3 out here. So that's something for later. But with that being said, now let's try and simplify the square root of x to the 4th. And actually, x to the 4th, that's a perfect square itself. It's got a power that's a multiple of 2. So the square root of x to the 4th, just divide this power by 2, that's x squared. And now for the square root of y to the 5th, let's break that up. The largest multiple of 2 that goes into that is y to the 4th power. And y to the 4th times what will give us y to the 5th? Well, y to the 1st power, or just y. Now the square root of y to the 4th is the same thing as the square root of x to the 4th, just with a y this time. It's y squared. And now we're ready to combine everything into our final answer. Let's first take all the numbers that are not under a square root. So we have the 3, the x squared, and the y squared. And then we'll focus on the square root pieces. That's the 3 and the y. So here we get the square root of 3y. And right there, that is our answer for the first problem. Now moving on to our second problem, let's just repeat this whole process. Again, let's break this up into the square root of 45 times the square root of x to the 12th times the square root of y to the 9th times the square root of z to the 7th. And let's simplify each piece separately. First off, with the square root of 45, what's the largest perfect square that we can take out? Well, I'm thinking we can take out a 9. Because the square root of 9 times the square root of 5, right? I know 9 times 5 is 45, so the square root of 9 times the square root of 5 is the square root of 45. And this simplifies because the square root of 9 is 3, so we get 3 rad 5. Now next, this x to the 12th. Well, that's going to be a perfect square, right? This 12 is a multiple of 2. And if we divide it by 2, we get what the square root of x to the 12th is, which is x to the 6th. Next, we have that square root of y to the 9th. The largest multiple of 2 that we can pull out of there is an 8. We can pull out a y to the 8th. And y to the 8th times what is y to the 9th? Well, y to the first power, or just y. And the square root of y to the 8th, divide that 8 by 2, that's a y to the 4th. Lastly, we have the square root of z to the 7th. The largest multiple of 2 that can come out of there is z to the 6th. And z to the 6th times z to the 1st, or just z, is going to give us that z to the 7th. The square root of z to the 6th, just divide that 6 by 2. It's going to give us a 3, so z to the 3rd. And now that we have all of that done, we can combine that into our answer. Let's start off with those pieces that are not under the square root. So we have a 3, we have an x to the 6th, a y to the 4th, and a z to the 3rd. And now let's do the square root. Underneath the square root, we have a 5, a y, and a z. And that's going to be our answer. Now moving on to problem 3, now instead of having a square root, we have a cube root. So we got to see how that changes things. Now at the start, nothing was really that different. We're going to still split up the radical in the same way. We're going to have the cube root of 54 times the cube root of x to the 7th times the cube root of y to the 5th times the cube root of z to the 9th. And we got to start off by simplifying the cube root of 54. Now, before, what we were trying to do is we're trying to pull out the largest perfect square. But now since we're talking about cubes, what we're trying to do is we're trying to pull out the largest perfect cube. So we got to go over our perfect cubes. Perfect cubes are going to come from 1 cubed, 2 cubed, 3 cubed, and so on and so forth. 1 cubed is 1. 2 cubed is 2 times 2 times 2, which is 8. And 3 cubed is 3 times 3 times 3, which is 27. And I recommend you memorize these 5 perfect cubes: 1, 8, 27, 64, and 125. Honestly, first off, 1 you really don't need to memorize at all. So really it's just these 4, and honestly you don't see 125 that often, so I would say it's these 3. So just make sure you know 8, 27, and 64. And if you forget them, you can always just do that exact same, 1 cube, 2 cube, 3 cube thing that we just did. So which of these numbers can we take out of 54? Or at least what's the largest number that we can take out of 54? I see this 27 right here. And 27 times 2 is 54. So we can divide this up into the cube root of 27 and the cube root of 2. Now, the cube root of 27, that's 3, because 3 cubed is 27. So we've already got that piece done. And now we just have to worry about all the variables. Now before, we were trying to take out the largest multiple of 2. That was with perfect squares. But now, since we're dealing with perfect cubes, you can probably guess, we're trying to take out the largest multiple of 3. Because things like x cubed, x to the 6th, x to the 9th, x to the 12th, and so on and so forth, all these x's that have powers that are multiple of 3s, these are perfect cubes. We can write x cubed as being x to the first power cubed. We can write x to the 6th as being x squared cubed. And it's self-explanatory for x to the 9th. From that information, you can see what the cube root of each of these pieces are, and to find that, like if we want to find the cube root of x to the 6th, all you have to do is take that power and divide it by that 3. Divide it by that root. And 6 divided by 3, that's 2. So that's how you figure that out. So what is the largest multiple of 3 that we can pull out of x to the 7th? Well, we can pull out an x to the 6th. And x to the 6th times what is x to the 7th? Well, x to the 1st, or just x. Now the cube root of x to the 6th, we just talked about that. That's x squared. Just divide the 6 by the 3. And then we have the cube root of x up here. Now next, we have to deal with that cube root of y to the 5th. The largest multiple of 3 that can come out of that is what? It's 3. And y cubed times what gives us y to the 5th? Well, y squared. So this is times the cube root of y squared. And the cube root of y cubed, 3 divided by 3, that's just 1. So y to the first power, or y. And then we have well, already over here for the z, we have that the 9, that's a multiple of 3. So we can just do 9 divided by 3, that's 3. And so the cube root of z to the 9th is z cubed. And now we have everything we need to combine into our final answer. Let's start with everything that's not under a cube root. That's the 3, the x squared, the y, and don't forget about this z cubed over here. And that's going to be multiplied by the cube root of, we have a 2, an x, and we have a y squared. There we go. Our third problem is done. Moving on to problem 4 here, we have a square root again, but we have a giant fraction to deal with. And so you might start to get cold feet here, you might start to get freaked out. But really, all we have to do is just simplify what's under the fraction first, and then we can start to break everything up and it's going to be fine. So first off, I'm going to simplify the numbers. I have 50 and 16. I know that each of these are divisible by 2, so I'm going to divide by 2 on top and bottom. And that's going to give me a 25 over 8. And from there I can't simplify anymore, so that's going to be the start of my square root. Now next I have to deal with these x's. I have an x squared divided by x cubed. And you could do subtraction of exponents like 2 minus 3 and say, oh, that's x to the negative 1, and if you think about that being over 1, then that's 1 over x and all that stuff. But honestly, there's a faster way to go about this. What we can do is immediately see that this is 1 over x to the first power, and here's why. Since the power in the denominator is bigger, to avoid the negative exponents, what we can do is we can do the subtraction of exponents in the opposite way. We can do 3 minus 2, and that gives us the 1. And since we did that subtraction of exponents the opposite way, since we did it from bottom to top, that means that we're going to put our answer in the denominator this time, not the numerator. That's how we can quickly see this is 1 over x. And that x is in the denominator, we're going to put that here. The 1 can go up here, but honestly, 25 times 1 is just 25, so we don't need to include that. Next, we have to do our y's. We can just do subtraction of exponents there. 7 minus 4 is 3, so this is a y cubed. And then we have z to the 4th, which does not have a counterpart, so it's just going to stay put right there. So now that this fraction is simplified, we can break this square root apart. And how I'm going to do that is we can write this as the square root of 25 times the square root of y cubed times the square root of z to the 4th all over the square root of 8 times the square root of x, and we can simplify each of these pieces separately. And what I'm going to do in order to make this nice and neat so we can do that is I'm going to take these guys, I'm going to put them right over here, and instead of having a horizontal line here, I'm going to put a vertical line, and this will be all the stuff in our numerator, this will be all the stuff in the denominator. So let's start off here. The square root of 25, we know that's 5, so that's a nice start for us. The square root of y cubed, remember, we are doing square roots now, so we're trying to find the largest multiple of 2 that we can take out. And the largest multiple of 2 that can take out of y cubed is y squared. And y squared multiplied by y to the first will give us y cubed. The square root of y squared is y. We circle rad y. Now we can move on to the square root of z to the 4th. Now, this is already a multiple of 2, so we know z to the 4th, that's a perfect square. If we do 4 divided by, remember there's 2 out here for square root, that gives us z squared. And now we just have to do our denominator pieces, the square root of 8 and the square root of x. Now the square root of 8, I know I can divide that into the square root of 4 and the square root of 2. The square root of 4 is just 2. And so I get 2 rad 2 off of that. Now the square root of x, I can't simplify that at all. That's an x to the first power, and I know that I can't take any multiples of 2 out of 1. So I'm done, and I'm ready to combine things for my final answer. So remember, this is my numerator, this is my denominator. We'll do the numerator first. That's going to be a 5y z squared. And I do have that rad y I have to include, the square root of y. And then, in the denominator, I have 2 times rad 2x. And this is where you have to be very careful. So some teachers are going to be okay with this answer, but some won't because they don't want to see a radical in the denominator. And so what you have to do here is you have to rationalize the denominator. You got to get that square root out. And so you can do that. It's pretty easy for square roots. You just multiply by that square root on top and bottom. Doing that, we get our final answer. We get 5yz squared times the square root. Now we have a 2x and a y, so that's going to be the square root of 2xy. And in the denominator, we have 2 times the square root of 2x times the square root of 2x. And when you have two square roots that are the same, the square roots cancel out and you just get the number that's underneath it. So square root of 2x times the square root of 2x is just 2x. So those two things give you 2x. If you multiply that by 2, you get a 4x. And that is what's going to give us our final answer. Now moving on to the last problem for this video. Now we have a fraction and we have a cube root. So we took the two gross things about the two last problems and we put them together all in one problem. But it's still really not going to be that tough. What we're going to do is we're going to simplify the fraction first, and then we'll go from there. So first off, the numbers, we just have a negative 64 here, and that doesn't have a counterpart in the denominator, so it's going to stay put. And then we have x to the 9th divided by x to the negative 2. That's just subtraction of exponents. 9 minus a negative 2. Let's draw that out. 9 minus negative 2. I see two negatives together. I make them positive, and that gives me an x to the 11th. Then I have a y with no counterpart, so that's going to stay put there. And I have a z squared divided by a z to the 5th power. And remember, I can do that subtraction of exponents backwards this time because I see that the power is larger in the denominator. All I need to do is just make sure that when I do the subtraction, when I do the 5 minus 2 and I get 3, I put my answer in the denominator. So now we are ready to break this cube root apart. I got to make sure I include that cube root there, and we can do that as so. We can write the cube root of negative 1. I'm going to do that negative separately from the 64, just so we can talk about that a little bit. So I'll have the cube root of negative 1 times the cube root of 64. And note that this is still fine, right? If you multiply these two, you get the cube root of negative 64 like we see here. This is times the cube root of x to the 11th times the cube root of y. And then in our denominator, we have the cube root of z cubed. So let's start going here. The cube root of negative 1, that's negative 1. And the reason for that, why is this not a big deal that we have a negative under a radical? Usually you're taught that you can't do that, right? Well, you can't for even roots. This is an odd root, and negatives are fine for that. Because you can take a number and multiply it by itself an odd number of times. Here, we're multiplying it by itself 3 times. That's an odd number. And that allows us to get a negative number out. But if we try to multiply any number by itself an even number of times, here we're multiplying by itself twice, that's an even number, we can't get a negative number. And that's why we can't have a negative under a even root. So for a square root, a 4th root, a 6th root, negatives won't work. For odd roots, they're fine. So we get negative 1 for that. The cube root of 64, that's actually a cube root we talked about earlier. That's just a perfect cube, that's 4. Now the cube root of x to the 11th, what's the largest multiple of 3 we can take out? Well, we can take out a x to the 9th. And x to the 9th times x squared will give us x to the 11th. So let's circle all of these. I'm not circling them, so I should probably catch up on doing that. The cube root of x to the 9th, that's x cubed. Do 9 divided by 3. That's how you get this 3. And then the cube root of y, I can't simplify that at all. That's already simplified because there's no multiples of 3 I can take out of 1. And then we have the cube root of z cubed. That's just z to the 1st power. So now I can combine everything into our answer. In the numerator, we have a negative 1 times 4, which is negative 4. We have an x cubed. And then we have the cube root. And the cube root is of x squared and y. In the denominator, we just have z. And I'll make that z look a little less like a 3. There we go. All right. And that is our answer for the last problem for this video. So hopefully now you're feeling much more confident when it comes to simplifying radicals with all these variables in them. And if you are, then here's a problem for you to try and answer in the comments. This problem looks gross, but it's pretty quick to solve. So try it out. Let me know what your answer is in the comments. And if you have any questions on anything we talked about in this video, again, let me know in the comments and I'll try to get back to you when I can. Now remember, I do have that extra video where you and I will go through and simplify 10 more of these radicals with all the variables in them. We'll do some problems like we did in the beginning. We'll do some harder ones with the fractions like we did at the end. So if you're looking to do some more practice, especially if you have a quiz or a test coming up on this stuff, I highly recommend you check out that extra video in the description. And while you're at it, definitely snag the notes for this video too. Lastly, make sure that you're subscribed to this YouTube channel. I would say more about that. I'd give you words of encouragement to subscribe, but I smell dinner downstairs, so I'm gonna get that actually. So that's gonna do it for this video, guys, and I'll see you soon.